Yep, welcome everyone to another talk from the DataLearning group. Today we have Peter Battaglia. He's a staff senior research scientist at DeepMind. He completed his PhD in the University of Minnesota and subsequently completed his postdoc in MIT. So Peter, I'll leave the audience with you.
Okay, thank you very much. And thanks for having me. So today the purpose of this talk is basically to cover a bunch of things that my collaborators and I have been working on, where we've been building deep learning models that are sort of heavily informed by physics, and we're sort of using them in physical problems. And then toward the end, I'll even show how we're sort of trying to kind of instead of modeling physical processes, try to actually discover equations and more sort of compact or general knowledge about physics. So the goal I have is to try to convince you of two messages. You might already agree with this, in which case I guess it'll be easy for me to convince you. But the first is that our knowledge of physics can improve our machine learning approaches. And I'll cover in that sort of in that direction. I'll talk about some of the work we've been doing on particle and mesh-based approaches for learning simulation. Also about inductive biases, or sort of structural constraints we're imposing on our learning architectures that have been motivated by ordinary differential equations, Hamiltonian Lagrangian mechanics. And the second sort of message I'd like to convince you of is that our machine learning tools can be used to improve our knowledge of physics. And some of the stuff I'll talk about here is how we use symbolic regression on trained neural networks to discover physical equations and also to discover sort of hidden parameters of systems that aren't directly observed. Cool. So before I get started, I'm going to just do a little bit of background. That's going to be sort of involved in a lot of the different projects that I'm going to describe. So my group, we work a lot with graph neural networks. So some quick background on graph neural networks from sort of our group's perspective. So you'll hear me say a lot of this phrase graph network. So graph network is basically a formulation of graph neural network. And the way a graph neural network or graph networks is it takes in a graph as input, and this graph can be relatively expressive. It can have, it can be directed. It can have attributes on the nodes and edges, or even graph level attributes. It can be a multi-graph. It can have multiple edges between pairs of nodes. And the idea is that this graph is supposed to represent some complex sort of system or some structured data. The graph neural network takes that graph as input, and what it does is it predicts a graph with the same structure but with different attributes on the edges, nodes, and graph level features. Now people use, just because it keeps the structure the same within the graph neural network, people in the literature often use these as sort of components of larger systems that can modify the structure of graphs and things like this. But basically, if you sort of just focus on this depiction I have here, I'm not sure if you can see my cursor, but basically the idea is that the edge, can you see my cursor as I'm moving it?
No, I don't think so.
No? Okay, I'll just describe it in words. So inside that blue box on the bottom left, you have this E that represents the edge attributes. The V represents the node or vertex attributes, and this U is sort of like a global feature of the graph. And the way the graph network works, it takes as input. But I'm realizing that actually the next slide probably is better for me to talk about this. So let me just go to the next slide. I'll describe exactly how it works. Okay, this is better. Okay, so the way that, so you see on the bottom left here, you see that graph network block, and I'm going to describe how this works. So first note in the bottom left of that block, you've got this phi e thing, and that's what we call the edge block or the edge function. And what happens is when the graph network takes in a graph as input, it applies that edge function to every edge in the graph. So if you look at on the top right, you see this blue sort of oval around a pair of nodes and the edge that connects them. This function phi e, which you see in the middle of the page here, sort of the top, phi e takes as input the edge attribute, the two node attributes for the sender and receiver nodes, and the graph level attribute, and it predicts what we call a message or a updated edge attribute. And we sweep this phi e function all over the graph. And what this does is so it's like sort of sharing the same edgewise function everywhere all over the graph. We compute messages between all of the nodes that are connected by edges. And then what we do is we aggregate up those messages for each node. Like for every node, we say what messages is it receiving, like which edges are pointing to it, and what are the messages associated with those. We average them up, and that's, if you kind of look in the middle of the page, this would be a lot easier if I had a pointer, but if you look in the middle of the page, there's an E with a bar over it, prime. That's the sort of like aggregated messages for one node. So to put this in physics terms, it's probably easier. If you think about it, it's actually a lot like classical mechanics. The edge function is like a force function. The aggregation of these messages is like superposition of these forces, that the forces that are incident on a body. You sort of sum them all up or pool them in some way. And then this phi v function is like an update to the body. So it's like sort of how does, if the forces are sort of incident on the body, on the node, it's like saying, how do we, the phi v describes how we would update the node's state. So it's like maybe like it takes into account like the node's mass, for example, and computes an acceleration, and then maybe predicts a new velocity for it. And this is like, even I'm using a sort of classical mechanics metaphor, it's really very similar to how this actually works. So these like sort of message passing neural networks or graph neural networks can be thought of as sort of communicating information around the bodies by the, according to what the edge structure is, and the edges represent interactions between these things. In fact, you can actually implement a a classical mechanical simulator as a graph network. You just don't use neural networks for these functions. You would just use like the actual force laws. And at the end of the talk, you'll see how we're kind of doing something almost exactly like that. Try to infer force laws. The last step of processing a graph network, which I should also say some of this stuff is sort of optional, which I'll get to in a second, but basically you have this global block that can pull up all the updated edge information and all the updated node information, and then update some graph level feature. And that's kind of the bottom row in this slide. Okay. And yeah, like I said, the phi E, the phi V, and the phi U we usually implement them as neural networks, which is a neural network is just a function. It takes some input and gives some output, right? It's got trainable parameters, so we can optimize its weights to fit various roles. The graph network that we are often using is something that we had sort of formalized several years ago, and we realized that it could kind of capture a lot of these other architectures in the literature, like message passing neural networks, and bottom left you have deep sets, or non-local neural networks, including like transformers or self-attention. Some other work we did several years ago on these relation nets. Basically, each of these models, these deep learning models on the sort of periphery, if you look closely, they're sort of like cookie cutouts. They have like some of the internal components to the graph network, but they're missing some. So we realized the graph network is sort of a generalization of all of these things. And if you just kind of cut some of the internal connections or remove some of the internal functions of the graph network, you get one of these other models. So it's sort of a very general expressive class of models. And like most sort of deep learning architectures and like engineering, you can compose graph network blocks just like you compose convolutional neural network layers or transformer blocks or MLPs and things like this. So you can, so on the left, I'm showing like you can have unshared graph network blocks where you have different weights per graph network, and it performs a sort of sequence of transformations on the graph's attributes over like a sort of chain of processing. At the end, you get out this GM, which is sort of like a final predicted graph. You can also have a shared graph network core, and that's in the middle. The idea is you're having the same weights, so it's sort of like a recurrent neural network or something. You have the same weights that are applied over and over and over again, maybe like kind of like an iterative algorithm, sort of. And then on the right, you have this encode process decode sort of arrangement of graph network components, which is sort of one of our favorite sort of kind of ways of designing and implementing our models. And I'll talk about this a lot more, but basically if the GINP, the graph input, is like some input graph. It gets encoded into like the input data gets encoded into some kind of high dimensional node and edge representations on the graph. And then you have some either shared or unshared processing in the middle, and then you decode out some prediction that's usually going to be fed to some objective function that you're going to want to optimize at the end. So it's sort of like a fancy regression problem. Your input is G input, your G out is the target, and then these gray blocks in the middle are like, again, some complicated nonlinear regression that you're going to optimize. Okay, so that's kind of like just some basics. I'm going to kind of walk through some of that again as I go through like the first thing I'll describe, which is like an application of graph neural networks to learning simulation. So here what we wanted to do is, like I said before, these graph networks are kind of like classical mechanics or, physical solvers. We take that very literally. So we like to say, let's just see if we can make these graph network-based architectures into physical simulators. Over the course of about like 5 years now, we've sort of started with very, very simple two-dimensional systems that we've simulated. And now we're kind of, we find we can learn to simulate very, very complex systems, which I'll describe now. So the way this works, you'll see this kind of regime that I'm about to describe several times because I'll go through a bunch of projects that use this sort of general research strategy. It's going to be a supervised learning problem where we're going to take in some input x t naught. That's like the initial conditions of some physical system. And what we care about is getting this S theta. So this is like S stands for simulator or learn simulator. And we want an S theta that's where theta is the parameters of this learn simulator. And we want this S theta that's going to be able to take the initial conditions and predict the state at the next time step. And the idea is we're just going to, if we can train it, because physics is sort of a process that's sort of stationary in time, meaning physics that happens now is the same as physics that happens now. We think we can apply the same function over and over again to its own outputs to just iterate, sort of unroll physics, or like produce a rollout of a physical trajectory in time. And the way we usually organize these learn simulators is we have like this dynamic. You can see in the middle of the schematic. It's this d theta is this dynamics block, and then we have some update function, which is like kind of like a numerical integrator usually. So the d theta is the dynamics sort of predictor. And again, the theta is the thing, the neural network parameters we're going to optimize. Okay, so here's how this works. So like I said, we have our sort of cherished encode process decode architecture where we take the input state of this fluid. And so again, this is going to be a fluid simulation of a particle-based representation of a fluid, Lagrangian representation. So again, like you have these blue fluid particles in the bottom left, where xi represents their like positions and velocities. We construct a graph out of that. So we say, what particles are nearby each particle, and we instantiate edges between them, because this is sort of how an actual fluid solver works. It communicates forces between nearby particles. So we encode this input x into a high-dimensional sort of latent vector, which is these v's. The 0 superscript just indicates that this is like the initial representation, latent representation. It's going to be evolved within the graph neural network's message passing in a second. But basically, you can see now we've gone from this sort of set of particles to this graph of high-dimensional representations of a particle. And then we apply a graph network block, and that's this processor sort of step where we say we pass messages. What happens is again, we take this phi function that I described before, we apply it to every edge. And then what it produces, we then pool up those messages on each node that is receiving them, and then make some update to the attributes of that node using this phi v function. And we just do this about 5 to 10 times. So you see the processor is repeated. Here it's m times. I think in practice we usually do about 10 times in this paper. And at the end, we get this processing chain, we get this GM, which is the sort of final internal process latent representation of the graph. And then it goes to a decoder. And this Y represents how we've decoded from some high dimensional latent representation of each node to, in this case, Y represents changes in velocity. In some cases, we use change in position, but change in velocity. So it's sort of proportional to acceleration. And then we can integrate and update the state, the positions and velocities using, in this case, an Euler update to get the state of the system at the next time step, xt1, basically. So that's the sort of general scheme. We just turn the particle as a set of inputs into a graph, propagate messages around it, predict some updates to all the positions and velocities. And we use supervised learning, which means we basically, because we have a ground truth simulator, we want to see if we can get the neural network to be as accurate as the ground truth simulator that's actually producing the data. So we just take the data trajectories from the simulator, cut them up into pairs of an input and then a next state, and then we impose a loss function on that y or the future predicted state that says that it gets penalized for the predictions from the model get penalized for deviating from what the true data set state is. And then we optimize, we backprop through the model, compute gradients of the loss with respect to the weights of the neural network, and then just push the weights around until they reach values that minimize the loss. So that's sort of standard backprop, stochastic gradient descent in deep learning. So if you know how to train a ConvNet or an MLP, it's very much the same thing. It's just a different set of internal processes. Okay, so when we do that, here's what we get. So these videos on the left, it's like the ground truth simulator. This was an SPH simulation 3D. The reason that there's like a sort of surfaces, it's like the liquid water, is because after we did the particle-based simulation, we just did this post-processing step just for the graphics to put like this kind of smooth surface over it. This is just in some standard graphics package. You should be able to see in a second, it's going to kind of change its representation into the actual particle representation. Let's see if it's on. It's a little choppy on my screen, so I'm assuming it's choppy on yours too. But yeah, you can see here it's sort of turning there. So it's sort of, oops, I'm sorry. Go back to the water. I'm just going to move this slider manually so you can see it. So you can see, like, here's the particle representation of the fluid here. And you can see you get very realistic and very accurate sort of fluid splashing behavior inside this system. Again, this was only trained on one step supervised training, but it stays stable and accurate over like 1,000 time steps. And there's 14,000 particles in this box. We can also do not just water, but other materials. So this is like sort of a sand-like material. This is not a SPH simulator. This is a material point method simulation, 19,000 sand particles, but sort of you get similarly accurate sand behavior. You can see some of the particle representation here. And then we can also do, this is our goop material that we simulate. We don't really know what it is, but basically, it's some kind of, gelatinous thing. And again, here's the particle-like representations of this material. So it's pretty accurate. Each one of these was a different model trained on these different systems. In this, I'm just showing how, so we also did some 2D simulations, which turns out in some cases are actually more difficult to simulate than the 3D ones. But the 2D is, we're showing this just to kind of show how we can get these sort of complex interactions between the rigid obstacles and this like flowing water. It's not just sort of simple box, but now we have more complicated arrangements of obstacles. And across the training set, there's different arrangements of these obstacles. We can also have a model that actually simulates multiple materials. Sorry, it's very choppy, but multiple materials at once. So this is a single model that's simulating sand, goop, and water all at the same time. And what's interesting about this is that we actually bought test time. So the reason that these models generalize is due to something that I mentioned before, that because these phi-e, like within the graph neural network, because the phi-e and the node updates are local, they're operating at the edge and the node level. This model doesn't know about what's going on in the broader system. These models don't have these global features, I should just add. So basically, when we train these phi-e and these phi-v functions, all it sees is this local neighborhood. So we can train it on small systems and have it generalized to much larger systems, much longer rollouts. And even here, there's sort of more complex interactions. At least the structure of the fluid and goop and sand is more complicated. So that's kind of a nice property that these are the sort of the reasons of why we want to build these neural network simulators, is because we want to see if we can get either efficiency advantages over hand engineered simulators like the traditional simulators, or maybe we can train on very small systems that would be sort of if we can get more efficient neural networks, then we maybe can train on small systems that would be prohibitive to simulate at a large scale. But then if the neural network scales better, then maybe we can run it at large scale inference time, despite that it never saw that, you couldn't do that scale at all in the traditional simulator. And I'll kind of talk about that in just a second. One other thing we can do, we can have rigid objects that are represented as a group of particles. And here we're not really doing anything special. We just sort of give each of the materials, I should have said this before in the multi-material thing, the way the model knows these are different materials is we just add an extra feature. So the particles have these features, position and velocity, but we also add on a new feature that just represents like the type of material. So it'd be like a 1 if it's a solid and a 2 if it's a liquid. And then that way the neural network can treat these particles differently. If it's a solid material, then it knows that it should sort of stay in the same relative relationship with its neighbors. And so you can see that simulation works. Cool. So, okay, so then here's another paper. So the work I just showed was work that we published in ICML last summer. This is work that was in, I guess I didn't update my slides, but this is work that was published at iClear 2021. In fact, actually won an outstanding paper award. So we're really excited about this. So here it's the same basic idea, except all we're doing is instead of having a sort of Lagrangian representation of a fluid, we have these mesh-based representations of these like sort of cloth, structural mechanics, compressible and incompressible fluids. And I'll show that model in just a second. But basically, if you look closely, you can see that like the dynamics in all of these are quite different. And in the two fluid ones that on the right, the aerodynamics and the compressible and incompressible fluids, here the mesh doesn't, the variable is the mesh doesn't change. The mesh stays fixed, but the states like the pressure and flow fields and stuff at the density at the mesh vertices are variables. Okay, so here's how this model works. So this is very similar to the one I described before. It's basically a generalization of the one I showed with the particle thing. So instead of in the encoder phase, just looking at each, like it's not the input is not a set of particles here. So the mesh actually represents a graph. So rather than just building a graph in the encoder that's like on the nearest neighbors around each particle, here we just use the actual mesh, the edges on the mesh to represent the input graph's edges. But because the cloth or all these different sort of systems can have things like self-intersections, like interactions that are not reflected in the mesh connectivity. So like where this cloth is bumping into this sphere or where the cloth bumps into itself, we need sort of collision edges. So there we actually go back and we do have nearest neighbors around the particles of the ball and of the cloth. So we have two types of edges here. So now this model has actually it's sort of like two graph neural networks that are computing mesh space edges, messages, and world, which we call world or collision space messages. And the details aren't really that important, but basically you can sort of run this in parallel and just aggregate these up to update each node's position. So the messages are calculated separately, but then the node updates are calculated by a single function on the basis of the different types of messages. We also do some things in here that are a little bit different, where because in mesh simulators, you often have things like adaptive remeshing and things like that. We actually also trained a separate model to predict what types of remeshing operations like the actual ground truth solver was going to do. And then we predict basically sizing fields, like what the sort of this influences sort of how the mesh connectivity will be changed as a function of the like state. So as the state evolves over time, you want the mesh to change its sort of resolution in different parts, and you can predict that, and then you can predict that and give that as input to our model on each step, basically. And this is just to kind of show that we can train neural networks to do the various parts of the solver pipeline, and in order to get the same sort of like benefits of doing adaptive remeshing. And one of those benefits, besides the fact that it's quite accurate, another benefit is that it's 10 to 100 times faster than the mesh solver on which it was trained. So now we're kind of getting into this regime where you might be able to actually train on an expensive simulator, but run at a much faster and get like, near accuracy levels that are like near what the traditional engine would have. So here's some videos of this. So on the left, you get the ground truth flag cloth thing. And on the right, you got the prediction with the learned remeshing. I think in this video, it might show what happens when you turn the learned remeshing off too, if I remember correctly. So if you just watch on the right So you can see the cloth is quite accurate. I know I was wrong. It doesn't have the non-limit remeshing in this one. Sorry, I thought I had the when we don't run the remeshing. This is the structural mechanics simulator. So this is some deformable solid. It's simulating a sort of metal plate. And then here are the fluids, the compressible and incompressible fluids. So like on the left, you have sort of like a air or something like that around an airfoil, and on the right you have something like water. It's like sort of cylinder flow with water. And you can see that on the left side of the aerodynamics, the left is the ground truth and the right is the prediction, and on the right side, the top is the ground truth and the bottom is the prediction. But in general, you see over time that these if it's not, the video is not too choppy on your screen, you can see that the heat map that represents I think these are velocities. In this one, we have the different states that they match quite accurately. Okay, we can also do all kinds of generalization here. So here's an example where we trained on this sort of flag in the top left, and we after training at inference time, we ran it with these different kind of more complex cloth materials. So on the bottom left, you can see we got like these 3 fish flags. On the bottom right, what you're seeing is where we generalized from this cloth training, the small cloth training, to a much larger like windsock thing. So you see this like we trained on a pretty small little mesh, but we were able to run it on a much larger one. And this is what I was talking about before, where we're sort of now moving into the regime where we might be able to train on something that's like prohibitively expensive to run at a large scale, and then because it's 10 to 100 times faster, then we might be able to still run a learn simulator at the scale that we really need. And this also starts to open doors into things like, well, can we coarsen the kind of granularity of the mesh further, or sort of subgrid style things, or like coarsen the time steps more, maybe have adaptive time steps, and we're sort of starting to explore these things now. The overall goal is just to see if we can get, if there's a good reason to replace sort of the sort of unpleasant or inefficient parts of traditional solvers with machine learned components. Okay, so that's the end of the sort of just the sort of mesh and fluid simulation stuff. I'll talk about another way that we are, so the thing I was sort of we were leveraging before was that there's this correspondence between the mechanics and the structure of the graph and the operation, the computations in the graph neural network. Here's another way we take inductive biases and impose them on these learned simulators in our graph networks. So on the left, I'm just showing a kind of crude schematic. I'm not a physicist, but so I think you might view physics as a slightly more complicated process than I'm just depicting it here, but this captures, I think, the important things is you have some input, position, and momentum at some time n, and then there's a physics, like sort of black box physics function, and then at time n+1, you have different position and momentum properties, states. So this is sort of like just a way of thinking about what, a physical process. So the stuff I've described before, I labeled it interaction net, but it captured the stuff I showed before, these graph net simulators. Everything we do, we always predict changes in either the position or the momentum or both. And we sort of add them to the input. So the graph neural network, you can see that the GN V sub V is predicting is taking the input position momentum and predicting a change to it. And so there's sort of like an Euler update that happens, and it's just sort of fixed. So it's like a residual update or just a change of state that's applied. But in actual solve, and like when you take an ODE and you numerically integrate it, what you actually do is you have a function that gives you time derivatives, and that's represented by this f sub q dot and p dot. So you have so you one hand if you want to integrate some differential equations, you have equations of motion, a model of the time derivatives, and the integrator can do things like sort of Euler is a very simple integrator, but more complex integrators might call these time derivative functions more than once in order to compute like intermediate steps and build up more accurate numerical integrations, maybe have like conservative properties that are symplectic, things like this, get more accurate sort of representations under different sort of schemes for doing a Taylor expansion on the underlying equations. Okay, so taking that, that's like, sort of how a simulator works. So we said, why can't we do that? Why don't we, instead of using the actual equations, the differential equations, why don't we train a neural network to predict the time derivatives directly? So here on the top, on the right side, you're seeing this like yellow box is like, how the ODE's time derivatives would be used, would be predicted by this sort of time derivative function. We're just going to use a graph neural network to predict the time derivatives. So now it serves as a function that we call multiple times by an integrator under different time stepping, different input conditions to build out its like next step prediction. Another thing we introduced was we said, well, we can exploit Hamilton's equation under like Hamiltonian mechanics, and rather than predicting the time derivatives directly, we'll predict a scalar function, and then we'll take the partial derivatives of that scalar function with respect to the input momentum and the input positions, and under Hamilton's equation, those will set them equal to the time derivatives of the position and the momentum, as you can see sort of in this bottom right. And that's a different way to sort of to build out these time derivatives. So again, rather than predicting the time derivatives directly, we'll predict the scalar and then take the partial derivatives. Okay, so we call that the Hamiltonian ODE graph network. I just pointed to some collaborators. So Kyle Kramer is the one who we were sort of in our discussion sort of gave us this idea, or we sort of led this idea and was a collaborator on this. This is also similar to simultaneous work that was done by Sam Bredanis. Hamiltonian neural networks. So he didn't use graph neural networks, he was just using regular neural networks, and we just happen to be doing this with graph neural networks. Okay, so the reasons you might want to do this are that you might get you might get some interesting properties if you impose these different inductive biases. So on the left, you got the ground truth, and then each of these other blocks, I've just isolated one particle. The blue is the actual ground truth particle, and then the red is like an overlay of the predicted trajectory over like hundreds of time steps from different models. And what you see is in this interaction network, which is a sort of like previous class of models, over time, there does start to be some discrepancy between the positions of the particles. Error accumulates over time, and they start to differ from each other. On the true Hamiltonian block, this is just if we actually use the true Hamiltonian. So there's no learning here. This is just if we actually integrate or use Hamilton's equations and then integrate. And on the right two boxes, we've got our ODE graph neural network and our Hamiltonian graph neural network. And what happens is we find that, especially for the Hamiltonian graph neural network, it stays very accurate over very long rollouts. And even the ODE one stays more accurate than just the sort of previous interaction network style ones. In terms of like results, what we see, so we measure two things, like the predictive accuracy of these models, just how accurately it predicts states, but also like how the energy, the accuracy of the energy over time. So on the left plots, you see in the blue, the gray bars are the true Hamiltonian, so sort of like, again, it's not, the true Hamiltonian is not perfect because we've integrated it with like some kind of finite time stepping, so it's not going to be perfectly accurate with respect to a very high resolution simulation. But the blue bars are then like our sort of previous interaction network-based approaches, and then again, the green are the ODE graph network and the Hamiltonian. You notice that the Hamiltonians has the best predicted accuracy, that's the left bar plot over time. It turns out the ODE graph network has actually better energy accuracy than the Hamiltonian, which is kind of surprising. But we weren't using a symplectic integrator, we were using RK4. So that isn't guaranteed to conserve energy, so that's probably partly why. When we did test the symplectic integrator with the Hamiltonian model, it did have better energy accuracy and conservation. One other thing on the right, these line plots, one benefit of using the actual time derivatives is that in principle, we can change the time step. So the blue lines are like the past sort of interaction network-based approaches, and that gray region that you can see, that sort of vertical gray region, that indicates the time steps that we trained our models on. So in the left line plot, what you're seeing is a very narrow gray bar, and so we trained the times that we trained was 0.1. The step was 0.1, some arbitrary time coordinates units, and you can see that the interaction network approach that we had been shown before, with it doesn't use the time derivatives directly, it's quite good at that. At test time, it's quite good at its accuracy on the y-axis is quite good with respect to and its predictions at that trained time step. But as soon as you go to different time steps, it's not very accurate because it's predicting changes in the position and velocity that would happen at a different time than we're testing on. But the red and the green lines are our OD, our OG. The green is the ODE graph neural network. The red is the Hamiltonian one, and you can see those do a lot better job generalizing to different time steps than it was trained on. And on the right plot, I'm kind of showing the same effect where we kind of broaden the range of time steps that we train on to try to give the interaction network style simulator a more experience with different time steps. And again, it works on the steps it was trained on, but it doesn't work very well as soon as you get testing on the steps that it wasn't trained on. And that's why it sort of error goes up when it's out of the gray region. So that's some benefit. We played all sorts of games where we trained on long time steps, short time steps, different integrators, or swapping out different integrators to see if we can at test time get like sort of better, accuracy or kind of control the accuracy. Cool. So, okay, so that's the Hamiltonian stuff. Let's see, I have about 12 minutes left. Let me, I'll just go through this briskly because I want to get to the last part. We also have a version, the Hamiltonian inductive biases. Once we did that, we're like, well, what about Lagrangian mechanics? Can we impose Lagrangian sort of, inductive biases based on Lagrangian mechanics to our sort of graph neural networks, or just neural networks in general? And sort of, I'm sure you all know this, but as a reminder, you have your Euler-Lagrange equations. They don't specify the time derivatives that you need directly, so you have to just do some matrix algebra in order to recover your time derivatives. So in the bottom row, you see for solving for the second derivative of the position, second time derivative of the position. And so what we're effectively doing is we're using a neural network to represent the Lagrangian, the scalar Lagrangian function. And then because in these deep learning software libraries like JAX, we have like powerful auto differentiation tools. So we can actually do these gradient computations very efficiently without having to write lots of code to actually do it. But at the end of the day, we have the second derivative position, and we hand that to the integrator, and then that's what's required to compute the dynamics, to numerically integrate to compute the dynamics. One key benefit of Lagrangian neural network is that you don't need canonical position momentum coordinates. So in the Hamiltonian, you need to know what the momentum, when you get your input state, you need to know what the momentum is so that you can compute the partial derivative of the Hamiltonian with respect to the momentum in order to compute the q dot, the time derivative of the position. But in the Lagrangian, you don't. And so that's kind of a key advantage. So on the left plot here, what I'm showing is the Hamiltonian neural network when you know the canonical coordinates, the position momentum. But the middle plot is showing, the orange line is showing the Hamiltonian neural network when you just do some arbitrary transform on the coordinates. You can see that it just does not do a good job of predicting the ground truth. This is, so I should say this is like this sort of this, it doesn't really matter, but it's this relativistic particle task. And the key thing is the orange and the blue don't match up in that middle plot. So the Hamiltonian neural network doesn't, handle arbitrary coordinates, and Lagrangian neural network does. Again, just because it's the intuition is that because the input state is like Q, well, you're computing the time derivatives of the Q. You just don't need to know anything about momentum directly. Again, you can. We've been having discussions with some of our colleagues that work on these other sorts of variants of Hamiltonian inductive biases and deep learning, and we and they are starting to find that we should be able to do different types of interrogation on the trained models to get things like momentum out, especially if you impose certain constraints. But naively, at least, there is an advantage to Lagrangian, which is you don't need to know the canonical coordinates. We also created Lagrangian graph neural networks because we like our graph networks. So this is just this discretized 1D wave equation. But now, so I should have said this, here in this previous plot, this was not a graph neural network. Here, the Lagrangian was just, this is like an MLP that was representing the scalar Lagrangian. Here, the Lagrangian is represented as, well, we have little Lagrangians all over the mesh, basically, or the 1D, discretized mesh. But again, the idea is that we can apply these Lagrangian sort of inductive biases to graph neural networks as well, and we get accurate simulations of these this 1D wave equation. Okay, So with the remaining time I have, I'll just talk about the last sort of thing. So, okay, so this is the part where, before I said we're going to talk about how we can use physics and inductive biases from physics to improve machine learning. Now we're going to try to use machine learning to improve our, to contribute to physics. Yeah, I'll just go through this kind of quickly, but basically, by leveraging this fact that I was talking about before, that the graph neural networks computations have this correspondence to force calculations in classical mechanics, we can take the neural networks that are trained as these edge functions, these phi-e's, and we can interpret them as the force laws. So it's a function, it's a sort of neural network, so who knows what these parameters mean. But what we're going to do is we're going to use a symbolic regression procedure to then sort of distill this neural network into a compact symbolic formula. Okay, and we're going to, the data sets we are going to use for this NERVS paper are this simple particle data set, which you're seeing this videos on the right, and also this like detailed dark matter simulation. This is in collaboration with Miles Cranmer and Shirley Ho and David Swergel at Flatiron Institute. Yeah, so the way this works is, I kind of already said this, but basically, this figure is actually kind of complicated, sorry. If you look at the third row, it's gray, you can see the edge model phi-e, and on the right it says compute forces. That's the main idea. So we're going to train this this GraphNet-based sort of simulator, but then after we train it to just predict rollouts, like I described in all the stuff I talked about so far in the talk, we're going to do a second phase where we take that edge function out and we do symbolic regression against it. And the way that works is, you don't need to read this, but basically the way it works is, so Miles actually wrote this symbolic regression package in Python that uses evolutionary algorithms to search a space of symbolic expressions that will fit some, that will fit some input-output pairs, like in a sort of regression regime. The way to think about it, the evolutionary algorithm, because the equations and like the parentheses can be viewed as like a tree, it's sort of building up this expression, this symbolic expression node by node and edge by edge, basically. So on the right, you see these like sort of branch selection, crossover, mutation. These are operations in evolutionary algorithms, and the result is that you're going to ultimately get a symbolic formula that that when you feed the input data, it predicts the, it sort of has a good match to the target outputs. Okay, so this is what I'll say something of why we do this in a second, but I'll just show you how it works. This is a sort of complicated video that Miles made. The key thing to note is on the very bottom, this sort of what you see is this kind of scatter plot with a diagonal line. What we're doing, this is basically showing that so one thing we do is in our message function in our graph neural network, we restrict it to be two-dimensional. So instead of having a high-dimensional message, this is a two-dimensional message, because we know, because here we're doing a 2D physical system. So we want each dimension to correspond to a component of the a component of the force. We want them to be orthogonal. We impose some further inductive biases, like that we're going to superpose it, like that when we take those messages and aggregate them, we're going to sum them all up. And we're going to also divide them by actually, sorry, no, that's not correct. So they're going to be proportional to either force or acceleration, and we're going to fit like the masses basically in order to sort of like we're going to exploit force equals ma to say, okay, like if these are the there's some scalar that modulates the force or the acceleration, it converts one to the other, so that when you're trying to make the update to the state via the acceleration, it's been scaled by some variable that's been applied to the messages. But anyway, what you're seeing on the bottom is basically how the true forces on the x-axis of those two plots have a perfect correlation or almost perfect correlation with the values that are on these messages. So what you're seeing here is that before we even do the symbolic regression, we're just seeing that the message vectors inside the neural network they're like equal to the force vectors up to some arbitrary rotation. This is just because it's sort of indistinguishable in this model. Then we apply symbolic regression, and what we get out is a force law that's consistent with the known force law that we actually imposed on the system. So on the bottom right, you see this like, you see this expression come out. Let me see if I can, it's here, yeah, oops. You see this expression comes out, and that is consistent with the force laws that we've imposed to create this simulation. Okay. So here's a bunch of expressions that we discovered. So we set up a bunch of force laws and then generated simulations under those, like just by hand. And then we looked to see if our neural network training and then symbolic regression procedure could recover those force laws. And indeed, we were able to. So this is a spring, a 2D spring. So there's a 1 over r squared force law. There's a discontinuous forces in 2D. And we can also apply this not to the forces, but we can use a Hamiltonian neural network and apply it to the Hamiltonian, play the same game, just do symbolic regression against this Hamiltonian. Okay, so this shows that we can discover compact symbolic expressions from detailed, through the trajectories of the sort of detailed simulations. We also applied this to these dark matter. This is kind of what we would expect. So this was an example where we actually took simulators that were built not from like by other means, basically, like other ways of sort of simulating these dark matter halos, and then we were able to extract expressions. We've now taken symbolic discovery thing, and instead of doing it on simulations, we're doing it on real data and seeing if we can recover force laws from actual observations. So what we did was we took, we're going to do this with orbital mechanics. We're going to do this with our solar system. We're going to look at the trajectories of the actual planets and moons and other bodies in the solar system and see if we can recover the force laws that we know are like the governing equations of the solar system. In particular, like Newton's gravity formula. We also are going to do things like I said before, we fit a scalar that's going to be modulating these forces to produce the accelerations. So we're going to say, well, we're not going to give the network the actual masses of the planets and the moons. We're going to see if we can fit those. And the idea is that if we can accurately fit a simulation, we have a scalar that modulates these forces that and turns them into accelerations, then those are sort of equivalent to what a mass, like what mass is, the concept of mass in classical mechanics, and sort of exploiting F equals ma. Okay, so here's what we do. So the data set is this NASA Horizons data set that has 33 years of trajectories of 31 bodies in the solar system. The trajectories include position and velocities that are recorded every 30 minutes. We just divided the data set into 30 years for the training set and then 3 years for validation. And what we do is we build a graph that represents the bodies in the solar system where the edges connect all of them because they can apply gravity to each other. We run this through a graph neural network. In particular, this phi function. Now we only have one trainable. I don't need to get into details, but we don't even need a second neural network to update the positions. We just sort of do that by hand, or we just treat those the scaled forces as the accelerations directly. So we don't need an integrator. And then this phi is like the phi e from before. This is the message function within the graph neural network, which we also know has this sort of correspondence to what should be computing forces. So the first thing on the right, we're just seeing the trajectories from the data and from the learned simulation. So the data plot there is actual trajectories of some of the planets in the sun and the solar system, and on the right we've got some of the rolled out trajectories from the learned simulator. So we generally see that there's good accuracy. So we were able to learn to simulate the system. Then what we do is we look at the masses of the objects of the planets and the moons. They're all relative masses because there is no, like, they're all relative to the sun, basically. There's no like sort of absolute units of mass. And we find this plot's actually a slightly older plot, but we find some interesting things. So what you find is that by and large, the masses of the stars, the blue stars represent the true masses, and the orange hexagons, the pentagons represent the fit masses. So for the most of the planets, like Jupiter and stuff like that, they're quite accurate, the masses. What aren't accurate is like Mercury, Venus, Mars, and this makes a lot of sense because these planets don't have moons. And because they're not influencing anything, it's very hard for our system for our approach to do the system identity. It's like sort of unidentifiable. How could you know how much mass a planet has unless you see how it influences other things? And so we would not expect things like Mercury, Venus, and Mars their mass estimates to be very accurate. We also see this with certain moons that are far away from anything and don't seem to be interacting with things very much. So this is actually, even the errors between the predicted and the fit and the true masses actually are exactly what we would expect, because we should not be able to identify them just from the basis of how they've influenced other trajectories. So this is showing we can discover hidden physical parameters from real observations, and this is basically my last slide. I'll show we can also discover the true Newtonian force law, gravitational force law. So we do our symbolic regression on this data, and on this plot on the bottom left, what you're seeing is these like teal bars on the right those are, when we run lots of symbolic regression or different randoms, these are like the sort of scores and of the different equations that come out, and you can see that across every symbolic regression run we run, it's always the true Newtonian force law, which is what this teal one is down here. You have to believe me, it's an R cubed. It is correct. It's just because there's an X in here. It's the way the symbolic regression works. So we always are able to recover Newton's gravitational force law. It's kind of cool because we're using I think it's like second and third law of motion to actually for Newtonian gravity. So this shows that we can actually discover symbolic expressions from real observations. Now the next thing we're trying to do is find things that we don't know the symbolic expressions for and see if we can recover them. Anyway, so this is it. So I tried to convince you of two things: that our knowledge of physics can improve our machine learning approaches, and also that our machine learning tools can improve our knowledge of physics. And I think hopefully we're kind of on that path. And yeah, that's it. So if you have questions or comments or criticisms, I'll leave with my collaborators. And if you, I can give you this slide. This has links to the code bases for the different projects and some of our like graph building libraries released. And that's it.
Thank you, Peter. Very, very interesting and a nice overview of the work you've done. If you have any questions, please raise your hand in chat, and I'll ask them for you. Any questions? I can start with one in the meantime. In terms of how many particles what are the limitations in the number of particles you have to deal with? And for example, the particle hydrodynamics simulations.
I don't think that there is a limitation, honestly. Like, so the ones I think I showed plots of 19,000 particles in that paper. We actually, at inference time, so we trained a small, we train a small numbers of those, but we think about 140,000 particles. But we don't think that this is what we, can comfortably fit in like the, on the hardware. We've also done, so some of this stuff like does take some pretty careful engineering, and like some of these larger systems, what you need to do is break up these graphs and put them on like different GPUs or TPUs in order to actually train them, because there's so many. But we can do that. So we can, like, if you have a large cluster and you have like inter-device communication, you can just split up your graphs and just have them, have a single graph split across lots of machines. And I guess machines you have, we haven't really pushed it. I mean, but there's no real reason why it shouldn't just scale sort of, up to whatever you want.
Okay, I guess we'll do
everything's local, right? So like local computations, everything's kind of local.
And do you think will you reach a point where like trying to run the simulation of the simulation, it will take more computational power than the actual simulation? So
that's what we hope is not the case, right? So we saw in the mesh version. So okay, I should have said in the fluid particle one, it's a little bit hard to measure to compare the speeds of the simulator, the neural network simulators to the traditional simulator, because the traditional simulators are like built to run on like CPU and like CPUs, highly optimized for CPUs. All these deep learning things, because they're doing all this matrix algebra, they're built to run like GPUs and like these TPU tensor processing, highly parallelized hardware. So it's not really fair, I don't think, to just like, you kind of have to like take your budget into account. Like, how much did you pay for your machine, right? But when we try to draw like an apples to apples comparison to say like how much like, per dollar of like hardware, if we kind of match them, which one's faster, particle one was about equal, we think, to the the traditional engine, and the mesh one was about 10 to 100 times faster if you again match the cost of the hardware. So, but this is because there's like the traditional solvers doing like lots of sub-stepping and things like this. That now we have sub-stepping too in some sense. We have like 10 message passing steps or whatever it is, but they'll often have much more sub-stepping, or they run at a finer time resolution. We often coarse in our time because again, these neural network functions in principle they don't have to learn the actual equations of the governing equations. They can learn some, some approximation that works well at whatever resolution we're training it on, hopefully in principle. Same thing with space. Like we're looking at how we can discretize space more coarsely. So this paper that I mentioned before the talk started, when we were just chatting, we have been modeling astrophysics. The main things we've been doing is trying to reduce the resolution of the simulator to much coarser resolution and see if we can make it much faster. And often we can, in principle, we can get like preservation of high frequency information in turbulence for I think it's like an order of magnitude or like an 8-fold reduction in like memory and compute. So this works learn complicated functions that allow us to take longer steps and have coarser spatial resolution. But it's sort of work in progress. We're kind of that's the goal right now. We're sort of in between getting there.
Yeah, no worries. That's clear. Yeah. Leszek has a question.
I think, yeah.
Sorry. Yes. I wonder whether graph networks are relevant to workings of human brain. This what is called folk physics, which allows us to drive a car or know what happens if we tilt a bucket of water. Do you think it's a better approach to explaining how human brain works, or have you got any opinion about it?
Because I've done the work in cognitive. This is like a lot of the work that's done in cognitive science is done by me in my previous life as a cognitive scientist. So in fact, that's like a lot of the motivation of this work. When I was at MIT doing a postdoc working with Josh Tenenbaum, and we were modeling human intuitive physics as like some sort of internal physics engine in your brain. We have papers on how people predict fluid dynamics as like some type of particle-based simulation they're running in their brain. But when I went to DeepMind, I was said, what I felt was that like we could use off-the-shelf physics solvers for the cognitive models. We didn't really believe that it has this SPH or this particular thing. The question is like, what type of physics engine is in the brain? Because it doesn't really have like the full resolution of the full state like a normal physics engine has. You seems to be able to make very good predictions. Like if you're going to throw a cup of coffee, you kind of know where it's going to go, but you also don't have this like fine grained information. So the question is like, what type of physics engine is in the human brain, right? Now, when we started off on this line of work, we were like, I was saying we're going to build like neural net. At that point, there was no machine learning physics engines. Like some of the work we did was some of the early work in this, and then we kind of building it up. But I don't think it was a question. I think we've gone actually a lot more toward physics solvers, like normal physics solvers, than actually getting to the question of, are these types of models that we're using, would those be good accounts of like the type of computational, or whatever those that are in the human brain? I think the answer is no. But we are thinking about this, and I think what you want to do is think about like hierarchical simulations that can represent the system at So there's one thing I've sort of, this is an example I often use, is like when I ask you a question of like what's going to happen, if I say like what's going to happen if I throw this phone or if I like pour this water, what you do is you give me the answer that's going to be about 80% correct. So almost like you choose the resolution of answer where you're going to be about 75 or 80% correct or whatever. So a very like unpredictable area, the phone's just over there somewhere. But if I'm kind of like pouring the water very carefully, you can give me a pretty good indication of where the water will and won't go. And to me, that suggests that we must have at least an ability between different levels of resolution, maybe like as a function of the uncertainty we have. So as our forward predictions start to become less certain, we may go up to a coarser granularity because it's just simply not worth simulating at a fine-grained level where it's just all noise. So we do not have these types of things in any of the models, but I'm sort of excited about this direction. Was one of the original motivations. But yeah, like I can't. So sadly, I would say it's not a good account of what's going on in the brain, but I do think that it's it's something that we're quite interested in. It's just funny that you asked that.
Okay, thank you for this explanation.
Peter, do you have time for another last question?
Yep, sure.
Yeah, Tico.
Yeah. Thank you. Thank you very much for the nice presentation. I had a question about the mesh graph, and then in particular, you mentioned some things about coarsening or sort of selecting the coarseness. I was curious how this would work out in practice. Does this have to do with uncertainty you just mentioned, or do you need some kind of regularization or kind of trade-off the computation?
Yeah, so I'm not an expert in this. This was the person who really knows the most about this was the first author of the paper, Toby Pfaff, he actually does PhD in graphics, and in fact in like adaptive meshes and stuff in physical simulation and graphics. So he's like an expert in this. But I'll give you my sort of best understanding. So in these cloth simulators and mesh simulators that we were using, there's heuristics that predict what's called a sizing field, and the sizing field is basically like it's sort of like a threshold for how finely to discretize, so to speak. So it's like if if it says that it can use a very coarse mesh because not much is happening, but easy to predict, then that'll be reflected in the value of the sizing field. And if it's like if it's sort of at some boundary or some kind of complex sort of dynamics are happening, it'll predict it'll predict you need to find a resolution. So the point is that you can, I'm not sure if my videos are going to show this. They probably, they must, I guess. If you look at the, let me just see if I can get it. You might see the mesh actually changing over time as you get into the mesh. So I'll kind of do it with this one on the bottom left. Yeah, if you look closely, you'll notice that the mesh is kind of like fluctuating. Like the mesh is not it's moving. It's like you can actually see that the edges and the nodes are changing in certain regions. You might also see it.
And this is then based on sort of hard-coded heuristics.
Yeah, so we didn't do anything that was too clever here. What we did was we just took the heuristic predictor from the physics, the solver, and then just tried to duplicate it. It was more of a proof of principle that could predict mesh things, but the real thing that we would want to do is we would want to train it not by supervising on the ground truth mesh, the ground truth remesher, but we would want to like use something like RL or like some type of training procedure that can operate in non-differentiable regimes because you're changing an actual structure of discrete variables. You'd want to like give it rewards for choosing meshes that are going to give you high downstream accuracy with low compute costs, right? You want to strike a good speed accuracy trade-off, which is what heuristics are designed to do. You want to learn a new heuristic, but we haven't explored that. We would like to.
Thank you.
Yep, that's the final question. Thank you, Peter, for your talk. Thank you for sharing your time with us and sharing your work. Yep.
Thanks for having me.
Yep. Goodbye, everyone. Thank you for attending.
Thank you.
See you later. Bye.
Bye-bye.